Okay, so far we've learned in this chapter we've learned about this rotational motion along the edge of a circle like this, right? Where this is your r vector out to the edge of the circle, and your particle moves through some angle to some final r. We can call this the r initial vector, and this the r final vector. And this path length right here we call s. Call that length s there. And we're going to give this the angle theta. And so far we've said that if we travel through an angle of theta, then the distance we're going to travel, s, is equal to r times theta. The distance along the edge of the circle. Right? And then also we say if we move through a certain amount of theta, d theta dt, in a certain amount of time, then we're going to call that omega. That's going to be our angular velocity. And if we're going along the edge of the circle, d theta dt actually ends up being, well, we can use d theta dt if we plug theta equals s over r into it, for example, into d theta dt, we get the tangential velocity equals r times omega in the end. So this is the tangential path, or the path along the edge of the circle that we travel, the distance along in that path. This is the speed that we're traveling along the edge of that circle. And notice what we've got. The angle, r times the angle. Angular velocity, r times angular velocity. Can you make the next guess? If you take the time derivative of the angular velocity, you get, what do we get? You get the angular acceleration. We call it alpha. We give it the Greek letter alpha. And if you wanted to know the tangential acceleration along the edge of the circle, how do you think you would calculate it? R times alpha. It turns out that the pattern holds. So this actually is very important to remember. I'll show you in the book where they write this all down in one place. We'll see that in a minute. But anyway, this is very important to remember because this is actually going to help us to convert some things. In this realm over here, we can use linear kinematics over here in many cases, which we already know how to use. You know, velocities, distances, accelerations, whatever else. On this side, you can use this stuff with S and VT and AT because it's kind of like linear stuff. I mean, it is following curved paths, but as long as you remember that you're following a curved path, you can use it. And also, there are many situations where something curved translates into something linear, quite literally. And so you can actually use it in those situations too. For example, when a wheel rolls along the ground, the tangential path, or let's say the tangential speed or the tangential velocity of a point along that wheel is equal to the velocity of the car moving forward. How fast a point on your wheel rotates is exactly the same speed as your car moves forward, as long as your wheels don't slip. Right? So there's an example where an angular velocity, let's say if your wheels are moving at 50 radians per second, or something like this, you could put 50 radians per second into this and calculate omega. Well, that is omega. And then multiply it by the radius of your wheel, and you would get your actual speed of your car. In fact, that is exactly how your car calculates the speed of your car. Okay, the speed of the car is calculated. Every car has certain size wheels that it's supposed to use. And that's not because if you use a different size wheel, it's going to break the car. It's because if you use a different size wheel, you won't know what speed you're going. Okay? So as long as they fit on your rim, you can use any and fit in the wheel well. You can use any size tires you want. But if you don't change your speedometer will not read it properly if you can't change that. Newer cars now actually have built-in GPS, and they can use that to determine their speed, but I think they usually still have a built-in speedometer that is based on wheel size. Anyway, so let's go back to here. So there's your tangential velocity, and then of course the last one that we talked about already. Oh, and of course the velocity also has a vector equivalent, an equation that is the vector equivalent. So just like before, the angle vector theta is always 90 degrees, well, is 90 degrees to the plane that the angle is in. So our circle is in the XY plane. So if we put the XY plane down here, X and Y, then the theta vector will actually come up into the Z plane. In this picture, it would be coming out of the page in the Z plane. And the way you determine that, again, is you take your right hand and put it on the x-axis, you turn your fingers towards the theta, the angle in the direction your angle went, and your thumb will point in the direction of the direction of the theta vector. So this theta vector, if you put your hand down here on the x-axis, you turn it towards the r vector, this is where the theta is, so you turn your hand this direction, your thumb will point up, and that's in the positive z direction. For omega, the angular velocity, it's very similar. For omega, you're going to put your hand on the r vector, and you're going to turn your hand in the direction of the tangential velocity. It'll tell you which way it's going, and that will tell you the angular velocity. Or if you want to do it if you want to do it in the other direction, you can put your hand in the direction of omega, which will be the same direction. It will be the same direction as your angle vector theta, unless it is slowing down. If it's speeding up, it'll be in the same direction. Unless your angle is going the other direction. So if your angle is going counterclockwise in the XY plane, then it'll be in the Z direction. If your angle is rotating the other way, clockwise, then this will be pointing down in the Z direction. And we'll get lots of practice doing this. Well, not lots. We won't spend a lot of time dealing with this, but we will get some practice doing this so that you can kind of get a feel for it. Again, this is not something that we spend a lot of time dealing with, these vectors, but we do introduce them to you because if you go on in engineering or physics, there is a class where you will do almost nothing but this so that you can understand how things move in the real world. But anyway, how to make the calculations for things that move in the real world. So here they show two examples. Here the particle is moving towards the y-axis like our circle. So the omega vector is pointing in the positive z direction. Here the velocity of the particle is the opposite direction, so the omega vector is pointing down instead of up. It's pointing in the negative z direction. Thinking in 3 dimensions is extremely frustrating. So don't feel like you're the only one that would be frustrated by seeing these pictures and trying to visualize them and figure them out. You're not. It just takes time to get used to them. And we'll take as much time as we can without wasting time, but we'll give you as much experience as we can. In the end, this angular thing gives you the same information, or it gives you the same things that you need as the formulas that we've used. So let's do an example really quick. We're not going to do an example with vectors right now, but not anywhere really. The use of the vectors is actually most important just to kind of get an idea where things should be. You don't necessarily need them usually to make your calculations. But here they do show the angular acceleration as the second derivative of the angle in time, and the first derivative of the angular velocity, which is exactly what we'd expect to get your angular acceleration. And then down here they're going to show us that if you want to know the tangential acceleration, you just multiply the angular acceleration by r, just like we suspected. So let's do this example really quick. Let's see what it comes to. So we have a flywheel. Flywheel is essentially a wheel that rotates to store energy. Okay. So this flywheel is sweeping out an angle of theta. Sorry. They're doing this. That's a weird way to write this. They're saying that it sweeps out an angle at the rate of theta equals omega t equals 45 radians per second t radians. That is just the stupidest way to write this. They should have just written sweeping out an angle at the rate of omega equals 45 radians per second. So what they're really saying here is that omega equals 45 radians per second. So 45 radians per second is our omega. The wheel rotates counterclockwise when viewed in the plane of the plane of the page. So whenever you're looking at the XY plane, counterclockwise will mean a positive vector for your omega. In other words, your omega is pointing in the positive z direction, just so you know. They want to know what is the angular velocity of the flywheel, and they want to know what is the direction of the angular velocity, so you definitely need to answer that. That is the positive z direction, because it's moving counterclockwise. And what is the actual angular velocity? They've told us that. They've said it's 45 radians per second. This is a weird question. But in C it says how many radians does the flywheel rotate through in 30 seconds? Well, if it rotates for 30 seconds and it's going at an angular velocity of 45 radians per second, you can actually use kinematics to do that. And they actually give you a clue at the beginning. I guess that's why they wrote it that way, is so that they would give you this clue that theta equals omega times t, so that you could actually calculate theta for part C. That's fine. So you just take the omega that they've given, multiply it by the time in seconds, which is 30 seconds, and you will get the amount of angle that it goes through, which happens to be 1350 radians. And then to calculate the tangential speed, remember that tangential speed is angular velocity times r. So you just multiply by the radius of the flywheel, which happens to be 10 centimeters, convert that into meters, and that's what they do in part D. You think 1350 radians in 30 seconds? That's moving, right? But in your car, do any of you have a car with an RPM, a tachometer on it? What does it normally read at when you're driving? 2,000 to 3,000, somewhere in there? Yeah. Depends on the car. What kind of car do you have? Yeah. So a Ford would be. Fords are usually a little bit lower in their. Yeah. And it really has to do with the way they've designed the engines. Japanese cars have a tendency to be a little bit higher in their RPMs. American cars tend to be a little bit lower. Can't remember Europeans. I think European cars have quite a mixture, actually, depending on where they come from. But it's usually been the case that American cars are a little bit lower, Japanese cars are a little bit higher, just because of the design philosophy. This right here, this number 1350 radians, if you remember, there's 2 pi radians per revolution, right? So if so 2 pi is about 6. If you divide 1350 by 6, you're going to get about that's about 200-ish, 200 and change revolutions. Sounds about right. Yeah, 200 and change revolutions. So this will be about around 400 revolutions, which, you know, is not a car's RPM, but it could be some other engine's RPM pretty easily, like a lawnmower or something. So that's reasonable, I think. So let's do another example really quick. Here we have a bicycle wheel. They put a bike on the repair stand and they start the rear wheel spinning from rest to some final angular velocity of 250 RPMs, and it takes them 5 seconds to do it. Now, here they're actually starting us into kinematics, but they haven't actually told us what the kinematics of rotational things are. So we're going to actually change. Before we do that example, we're going to change gears a little bit and go to section 2. Why? Because if we know how to go from theta to S, and we know how to go from omega to V, and we know how to go from alpha to A, just by multiplying by R each time, right? Then we can actually rebuild all of the kinematic equations. And they spend a lot of time doing all this. They do it algebraically first, and then they do it also using calculus. And I won't take you through all the mess of it. It gets a little bit messy, but in the end, it's really quite simple. You actually end up with the same kinematic equations that we did for linear kinematics. If I can just find it here. Here we go. So here's the table that I told you I'd find for you. This table tells you the linear variables, x, v, and a, and the rotational variables, theta, omega, and alpha. And then they have another one here probably that should tell you, here we go. So, and these are the relationships between theta and s, omega and v, and alpha and a. But this right here is a table of the kinematic equations. These are the ones you're used to, the translational ones. We've done these before. If you're doing angular stuff, these ones are your kinematic equations, but they're the exact same equations. You just replace all your x's with thetas, you replace all of your v's with omegas, and you replace all of your a's with alphas, and you have now the rotational kinematic equations. And they work the same exact way as the kinematic equations in linear dynamics. It's just rotational dynamics. You do have to remember, however, that in linear kinematics, the kinematic equations were only good if you had a constant acceleration. So in rotational kinematics, it's only good, these equations only work if you have a constant angular acceleration. The angular acceleration cannot change. It has to be a constant. If it's not constant, these equations go to Ichi double hockey sticks. So let's go back to chapter 1 and finish our examples, because this last example actually uses those equations. I don't know why they don't just teach you them first and then give you this example. But, so here a bicycle mechanic is putting on a bicycle wheel, and he's accelerating that wheel, and he's going to accelerate from a rest to a final angular velocity of 250 RPM in 5 seconds. Remember that RPM is not the units we want. RPM is incorrect. We want to, because that's rotations per minute, we want radians per second. So there are 2 pi radians for every revolution, and there, of course, 1 minute to every 60 seconds. So in the end, when you do that conversion, you have to multiply by 60. No. You have to multiply by 2 pi and divide by 60. Does that sound right? Yeah, that's right. Yeah, you have to multiply by 2 pi and divide by 60. I think that's what I said. But anyway, that's how you convert your RPMs to radians per second. So they do that right here, RPMs to radians per second. And then we know, of course, that alpha equals delta omega over delta t, so we have 250 RPM over 5 seconds. And if you do that first, you get 250 divided by 5 is 50, right? But if you do this first, you get 250, you end up with 26.2 for your delta omega, and then you have to divide by 5 seconds later. Either way that you do it, it doesn't matter if you convert before or after, you're going to end up with the same thing, which is an angular acceleration of 5.24 radians per second squared. Then, in part B, the bicycle mechanic hits the brake, and they put an angular acceleration of negative 87.3 radians per second square on it. You want to find out how long it takes the wheel to stop. So our change in time is going to be our change in angular velocity, which is negative 26.2 radians per second because it's slowing down. That's why there's the negative, divided by the angular acceleration during that time. So this is actually a kinematic equation right here. So is this one. But this is the same equation rearranged, and when you do that, you get the 0.3 seconds here. So it's nothing different. The only thing that's different here is we're dealing with angular variables instead of linear variables. Instead of x and v and a, we're using theta and omega and alpha. Now, what is the same between these two things, between these two systems of kinematic equations? Well, there really are two things that are related between these two systems. First of all, if you have a system that has both rotational stuff and linear stuff going on, then the time is always the same, right? Because time doesn't care if it's rotating or going in a straight line. Time just kind of does what it does. So the time will be the same for both systems. And if the rotational thing, if the thing that's rotating is causing the linear motion, then there's the relationship where all of the linear variables are equal to r times all of the angular variables, just like we've seen before. So important to remember those things once again, and I'll point that out to you again and again and again as we go through these examples. So here's another example of some kinematics. We have the wind turbine, has a radius, it's going along and along, and it takes 30 seconds for it to come to a complete stop. And they actually are going to give us a formula, well, a function for our omega this time. This means that our angular velocity is not constant in time. And it also suggests that our acceleration is not going to be constant in time. And actually, if you do this, this works out to be a quadratic, so it definitely our angular velocity is not constant in time, and our angular acceleration is not constant in time. So for this problem, we cannot use any of the kinematic equations, but we can use some of the things we do know. So they want to know, first of all, what are the directions of the angular velocity and the angular acceleration vectors. So what is the direction of this? Well, if we consider this our plane here, and we put our hand in, so for the right hand rule for this, to figure out the direction of omega, you'll use your right hand and you'll curl your fingers around in the direction of omega, with your thumb out like you're waving at somebody, right? Your thumb will point in the direction of omega in that case. So since this is going around in a counterclockwise direction, then omega is coming out of the page. It's coming straight out at you. That's the direction of omega. And for part A, they want to know what's the direction of that, right? Since the turbine is running counterclockwise, the velocity vector omega points out of the page, right? Now, it is slowing down. So what is the direction of alpha? Your omega is going this way. It is going this way, so it's pointing out of the page, but it's getting slower and slower and slower, which means the amount that it's pointing out of the page is getting smaller and smaller and smaller, which means that what's that? That means the acceleration is negative, which means it's not pointing out of the page, but into the page, right? So that's the direction of the angular acceleration, because it's moving towards the page instead of away from the page. Very good. And then here in part B, they want to know what are the directions of the angular velocity and what is the average angular acceleration? So the average angular acceleration, you just take the total change in angular velocity and divide it by the time. So the total change is, you calculate this at time equals 0. So this right here becomes nothing, and you get negative 30 squared, so it ends up being 900 divided by 100, so it's 9 radians per second, in other words. So about 1 revolution every second, 1.5 revolutions per second, turns out. And that's going to go from 1.5 revolutions per second, or 9 radians per second, to 0 radians per second in 30 seconds. So you take that 9, you divide it by 30, you'll get your average angular acceleration. But then they want to know what is the instantaneous angular acceleration at time equals 0, time equals 15, and time equals 30. Well, we don't have the acceleration function, but we do have the angular velocity function. So we can take the time derivative of this function to get the angular acceleration function and calculate it at time equals 0 and 15 and 30 by plugging in those numbers. So just take, for part C, you take the time derivative here and plug in these numbers, which is what they do. Time derivative, plug in the numbers. All right. Man, that took forever to get through one section. Like I said, in section 2, they talk about rotation with constant angular acceleration. In section 3, they actually write out all those equations. But essentially, these things just become the kinematic equations. You get all the kinematic equations out that we did for linear stuff. And so here's a great example of how this works. A fishing line on a fishing reel. When the fishing reel is turning, the line is moving either in or out, right? Oops. So the line is moving either in or out. Here you have rotational motion of the fishing reel translates into linear motion of the fish line when it comes off the reel or goes back on the reel, one or the other. So here you have rotational motion related to linear motion. And this is where you can use, if this thing moves through 2 pi radians, so 6 radians essentially, 6 point something radians. So if it moves through 6 radians and it has a radius, they're saying it's 4.5 centimeters, but I'm going to say it's just 4. So it has a radius of 4 centimeters. Then I take that 6 radians and multiply it by the 4 radius, and I get 24 centimeters of fishing line that comes off if I go through 6 radians. Because this radius times angle will tell you how much linear distance you went, right? And also, if I know that this thing is spinning around at 100 radians per second, if this thing is spinning around at 100 radians per second, no, that's too fast. Let's say it's spinning around at 20 radians per second, and it has a radius of 4 centimeters. Then I take the 4 centimeters times the 20 radians, the omega times r, and that will give me my velocity of the string coming off, my tangential velocity. So that would be 80 centimeters of string coming off the line every second, which is completely reasonable. About a meter of string coming off your line, off your reel every second. Yeah. So you take those angular things, you multiply them by the radius, and you'll get the linear things. If you take the linear things and divide by the radius, you'll get the angular things. And that's what this example is about. They're going to have you go back and forth with those things. And I will leave the rest of it for tomorrow. I mean, not tomorrow, Monday. We'll come back to this Monday. I will try to get some homework posted for this chapter starting today, but I'm going to guess nobody's really going to look at it till Monday anyway. So we all take a break. Have a good one. Oh, stop video. Yes.